All right, 1.9, we are going to be working with inequalities. So I'm going to go over a couple rules with inequalities, then we'll see kind of how we graph them, and then we'll work on solving multi-step inequalities. So today we are solving and graphing multi-step inequalities so that we can find and represent solution values on a graph. And you'll be able to do it when you can isolate a variable and represent its solutions on the graph. So it's getting the variable by itself and then representing it on the graph. So there's a couple important things to talk about with solving inequalities. We're going to treat them just like equations or equalities, right? The difference is that we have inequality signs. On our inequality signs, this is just a little note here at the top. I'll do this in blue. We have less than, greater than, and then we have less than or equal to, which includes the value that we're talking about, as well as greater than or equal to. So think about if I have x is less than 4, then we're not including 4 in our set of numbers because it has to be numbers smaller than 4. Versus x is less than or equal to 4 means that we can also include 4. And we'll talk about what that looks like on a graph. Okay, so another concept that we need to talk about, we're going to do this here in the first box or in the first set, multiplying or dividing by a negative number. So when we multiply or divide by a negative number on both sides, we have to change the direction of our inequality sign, or we'll flip our inequality sign. And I'm going to show you an example here in A of why that's true. So I'm just going to multiply by -1 to both sides. And if I multiply by a -1 to both sides, what happens is 4 times -1 is -4 now, and 1 times -1 is -1. So my initial statement is saying that 4 is greater than 1, which is true. It's a true statement. 4 is greater than 1. But anytime I multiply by a negative, it flips our statement. -4 is not greater than -1. Think about a number line. If we had a number line and I had -4, -3, -2, -1, 0. Think about on our number line, -4 is smaller than -1. And that becomes the case anytime we multiply or divide by a negative number. So it's a rule that we have to take our inequality sign and flip it to make the statement true. That's also true of using numbers greater than, or other than like 1. So I'm going to multiply both of these by a -3. -7 times -3 is +21, and -2 times -3 is +6. In order for this to be a true statement, we have to set our inequality 21 is greater than or equal to 6. And so this has to flip again. So that's just the rule. Whenever we multiply or divide to both sides with a negative, it's going to flip our inequality. Let's continue looking at this. This one will actually solve out. So for example, if I divide -2 to both sides to get x by itself, notice that I'm dividing a -2. So in order for this to hold true, our inequality sign has to change direction. So now it's x is less than -8. The same thing's true for if we multiply a negative to both sides. So if I need to get rid of this -5 by multiplying a -5, that's going to make those cancel out. And then I'm multiplying a -5 here. I'm left with x and -20. And my inequality, because I multiplied by negative to both sides, flips. It changes direction. So example E is similar to example C. The difference is that to solve this one, we are just going to divide a regular 2 to get x by itself. And the thing is, if we divide by a regular 2 or by a positive number to both sides, even though I have a negative up here, I'm looking right here at these two numbers that I used. If they're both negative, or if I use a negative here, then my sign flips. But if I use a positive number, my sign stays the same. So in this case, my sign does not flip because I used positive values here. In my other example, I used negative values, and so it flipped around. Okay, same idea here. In D, we multiplied -5 to both sides. But in F, we were multiplying a positive 5 to both sides. And even though there's a negative times a positive going on here, we look at the sign of the number we're multiplying or dividing to both sides to tell us what happens to our inequality. So these cancel out so that x is by itself. -4 times 5 makes -20. And our inequality stays the same because, again, these 5s were both positive. Okay, so that's the first concept. The second concept that I want to cover is graphing on a number line. And for most of these, you'll be given number lines to graph on. If you're not given a number line, like this is x is greater than 3, you can create one and you can just use that number and then a couple numbers larger. 4, 5, 2, 1, right? So x is greater than 3. So check this out. We're going to make sense of the inequality by making sure the variable is written first. In A, B, C, and D, the variables are all written first. But it's always good to check for that. So x is written first. And then we're going to determine if the circle, or the point that we use, is going to be open, which means if it's less than, greater than, or closed, which means it has that equal to line. So in this one, this is a less than. So we're going to have an open point on 3. I'll show that in red. So here's an open point on 3. And then we're going to shade either the greater than or less than values. And for me, if our variable is written first, I can use this kind of as an arrow. I know I'm going that way. So it's all of those values are greater than. That will work as long as your variable is written first. So x is greater than 3. We can read it easily, which means all of the numbers greater than 3 get shaded. So let's try this again. I'm going to create a number line here with 17. I'll use 18 and 16. We're going to determine, or let's make sure our variable is written first. It is. This is going to be closed because it has an equal to part to it. This little line underneath means it's going to be a closed point. It's including 17. So I'm going to put a closed point on 17, and then we are shading everything to the left. Okay, for C, we make sure our variable is written first. Good. Is this going to be open or closed? This one will be an open point on 6. So we're using an open point on 6, and we are shading everything to the left. For this one, variable is written first. Is it going to be open or closed? This one will be closed because, again, this equal to right here. This line down here tells us if it's closed. And then we're shading everything to the right. For these, example E, we need to flip this thing around so that x is written first. Notice when I flip it, my inequality is opening toward the x. It is, your little alligator, as people have talked about, is eating the x. So when I rewrite it with x first, I need to make sure that this is still facing toward the x, that it's still eating the x. Now that we have that, we can determine, is it going to be open or closed? In this one, it is closed. So I'm going to put I'm sorry, in this one it's open. I'm graphing and doing all kinds of stuff. In this one it's open because there's no line. And then we are shading everything to the right. Sorry for any confusion that may have caused. This is an open point. It does not have the or equal to line underneath. Okay, in example F, we need to rewrite this so that R is first. My little alligator, my inequality is opening toward the 6, so I'm going to make sure it's still facing the 6. It's still opening toward the 6. And now I can determine open or closed point. This one is closed because of this line. It is a closed point, and we are shading everything to the left. So that's graphing, okay? Let's take a look now at solving these. For solving, we follow the same steps that we use to solve multi-step equations. The main difference is we just have to be aware of any time we multiply or divide by a negative number on both sides, just like we did in the first part of this example here. So we will always look to distribute, then combine like terms, gather variables to both sides, use the inverse operation to get rid of whatever is adding or subtracting, and then the inverse operation to get rid of whatever is multiplying or dividing. And remember, if using a negative, flip the inequality. And then for graphing, we make sense of it by writing the variable first, determine if the circle be open or closed, and then shade either the greater than or less than value. So let's see how we can get through these. I'm going to do just some work up above and then some down below. So for this one, I'm going to add 6, and now I'm going to rewrite my equation b over 8 greater than 1. In order to get b by itself, I'm multiplying 8 to both sides. I'm checking to see if I multiplied by a negative. I did not, so my sign's going to stay the same, and b is greater than 8. So now I'm looking open or closed. It's open, and I'm shading everything to the right. All of that is my solution. Okay, for this one, we're going to distribute first. Negative 8 times b, negative 8b. Negative 8 times negative 2, positive 16. Greater than or equal to negative 72. This is a two-step equation. I'm going to get rid of my negative 16 first, or my positive 16 by doing the inverse and subtracting it. So I'm left with negative 8b is greater than or equal to, and these are going to add because they have the same sign. So we're going to end up with 88. We can now divide negative 8 to both sides to get b by itself. When we divide by a negative on both sides, our sign has to flip. So now it's going to be facing this way, and I'll work this out. b is less than 11. So now it's written the correct direction. Open or closed on 11 is going to be closed on 11, and we're shading everything to the left. All right, example C. In example C, I'm trying to get r by itself. The whole quantity is being divided by 3, so I'm going to have to multiply 3 to both sides. 3 times negative 6 is negative 18. These 3's cancel each other out to leave me with negative 3 plus r. Had I had a negative on both sides here, I would have flipped my inequality, but because they're both positive, I don't flip it. All right, so now I'm adding 3 to get r by itself, and that gives me negative 15 is less than or equal to r. Now I'm not ready to graph this because I don't have it written the correct direction, so I'm going to rewrite it as r is greater than or equal to negative 15. It's much easier to graph that way. I find negative 15 on my number line, put a closed point, and I'm shading everything to the right. All right, example D is similar to C, but we need to get rid of this -6 that's dividing. So I'm going to multiply a -6 to both sides. And then as I work that out, -6 times -2 is going to leave me with a positive 12. I'm flipping my inequality because I used a -6. I multiplied a -6 to both sides, so I have to flip my inequality. These cancel each other out, and I'm left with 5 plus x. From here, I'm allowed to subtract 5 to both sides, and I'm left with 7 is greater than or equal to x. I don't want to graph that way. I want to graph x first, or I want it to say x first, and make sure my inequality is still eating my 7. And now I can determine open or closed point. It's a closed point on 7, and I'm shading everything to the left. Any number that I pick in here, I could apply to x, and it would be a true statement. That's what this is saying. So if I grabbed a 5 and plugged it in, 5 is less than or equal to 7. That's true. If I grab a 0, plug it in, 0 is less than or equal to 7. That's true. If I grab a 7, 7 is less than or equal to 7 because it's equal to, that's true. All right, let's take a look at these last two. I'm going to distribute first. So 5 times 5r, 25r. 5 times 6, 30. In black, I will rewrite the rest of this, 6r less than -94. Now I'm looking to combine like terms. I do have like terms. My 6r and 25r, which make 31r. Now I have a two-step equation. I can subtract 30 from both sides. And that's going to leave me with -124. Signs were the same, so I had to add them and keep the sign. To get r by itself, I'm dividing 31. I do not need to flip my inequality because that is a positive 31 on both sides. And 124 divided by 31 is 4. So we are going to be left with, and it's negative. So -4 is less than r. And I don't want to graph like that, so I got to flip it around. R is greater than -4. That is an open point on -4, and R is all the numbers greater than that. But I can't plug in a -4. That's why it's an open point. If I plugged in a -4 is greater than -4, that's not a true statement. -4 is not bigger than -4. All right, and then finally example F. I'm going to distribute this negative in here, so I have -n and +1. I'm rewriting the rest of my equation. Make sure not to forget any negatives or any terms. Now I'm combining like terms on the same side. In this case, this is a -1n and a -8, which gives me -9n plus 1 is less than or equal to -27 minus 5. Now I'm 5n. Now I'm gathering my terms to one side. So I have variables over on this side and variables over on this side. So I'm going to get rid of the one that is less, which is -9, and I'm going to add that to both sides. Those cancel out. I have 1 is less than or equal to -27 plus 4n now. When I put these together, it made plus 4n. And now I have a two-step equation. So I'm going to add 27 to both sides. That gives me 28 is less than or equal to 4n. And then I'm dividing 4 to both sides to give me 7 is less than or equal to n. I don't want to graph like that, so I'm going to flip it around, and I'm going to say n is actually greater than or equal to 7. And then we're determining closed or open point. It's a closed point on 7. And we are shading everything to the right.